Let's compare that result to this variation of the loop. I've swapped the I and j around. And if we're adding up integers, then we don't expect this to be a different result. Our question is it a different performance result? So in this case, the first access is once again at I equals 0, j equals 0. That is a miss, which pulls a cache line in. The second time we get to the body of this loop, I will be 1 and j will be 0 still. And I1, j0, that's row 1, column 0, that's this next line down. That is a miss because the first hit only pulled in this first line. We're going to pull in a new cache line though. And it's still going to be a miss all the way down to here. What will happen to the next step when we go down one more row? It's still going to be a miss, but remember that the cache set for this bit of memory is the same as the cache set as that one. So in fact, we will not only have a miss, we'll flush, it'll replace the data that we had looked at before. We're not looking at it just right now, but there is going to be a problem. You can see it coming. That means we have misses all the way through down here. And when we get down to the end and start again at the top right here, it's going to be a miss again because it got replaced here. Because our array doesn't fit into the cache, and because we've accessed the cache this way, then we got a much worse miss rate. We got the worst possible miss rate. So what you can quickly see from this example is don't do that. Don't put the column access outside as the outer loop and the row access as the inner loop. Swap them around. Make the column the inner loop always. Right? And that corresponds to C being row major order. That means row is the major loop, the one on the outside. If we change our parameters of our cache so that we have twice as many sets, then we wouldn't end up replacing a cache line. Right? That's because the cache numbers would be 0 all the way through 64. In fact, we would get all the way to the end of the line, and we would have had a miss every time, so things are still looking pretty bad. But now, this time, since our cache is bigger, once we get to the end and go to the next access, back up here, it's actually in the cache, and it's going to be a hit. And in fact, this whole column will be a hit, and the whole next column will be a hit, and the whole next column will be a hit. In this case, we'll end up with a 25% miss rate again. And that illustrates how if your data all fits into the cache, it doesn't matter what order you do things in. It's going to be the best hit rate possible, which is 25% from a cold cache here. I note that this was one way of making the cache bigger. You see that it's 32 times 64. It's a 248 byte cache, which is why our grid exactly fits in it. We could also make the cache bigger by leaving the same number of sets, but increasing the associativity. In that case, our blocks within the data would be numbered still 0 to 31 and repeat 0 to 31. And yet we could still have this whole first column in cache because we have 2 lines in set 0 in our cache. And so we can keep both of these. And we have 2 lines at set 4 and so on. So the important thing is that the cache is big enough to hold the grid. Typical caches will increase the associativity instead of the set because that turns out to be more flexible when you have multiple arrays that you're accessing at one time. Here's another variant of our program. This time we have 2 loops. So we have adding up all the x's and adding up all the y's. So we have twice as many accesses. What is our miss rate per access? Well, we already know that this loop is going to have a 25% miss rate because we're doing it the proper way with the column access as the inner loop. This loop is also the same. So we have overall a 25% miss rate for twice as many accesses. But it turns out we can do better in this case. In this case, if we change the program so that we just loop over things once and accumulate x and y at the same time, it will be better. That's because we will start out at I equals 0, j equals 0, and we'll access the x part. That's a cache miss. But then, even before we continue the for loop, we will access the y part, and that's a cache hit. And in fact, the next xy, 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 those will all be cache hits. So we had only 1 miss out of 8 operations. That's going to give us a 12.5% hit rate overall, or a 12.5 miss rate overall. So even though we're doing more work, we don't have any more cache misses if we fuse these loops, which gives us a better rate overall, right? Which is one way of saying how this is a better program than the other program. Right? The general rule here is that if you have multiple loops that are going over the same data, if you can put those loops together and do the work at each element all at one time, then you can improve locality, you can improve spatial locality. And that's called fusing the loops, when we take two loops and glue them together so that they do their work at the same time. So just to summarize what we learned from this investigation, if you have a program that's walking over an array, then you want to make sure you're traversing a C array using the column as the enter loop, row as the outer loop, which is another way of saying row major. If your data fits in the cache, though, you don't have to worry about this. It's probably good practice, but if you know for some reason it fits in the cache, you can do whatever order you want. Meanwhile, if you have multiple loops, you should fuse them so that you get better spatial locality. We also saw that the best you can do, your optimal miss rate, if you're only using each element one time, is 1 over the number of elements per block. So when we had just 4 x's per block, because there's only 4 grid elements per block, we had 25% as our best ratio. When we had 4 x's plus 4 y's, that's 8 values per block, we considered it to be a 12.5%, or 1 over 8 ratio for that program.